The universe holds more questions than answers. What cosmic secrets will the year 2026 finally unveil? We are standing at the edge of a new era of discovery, where powerful new telescopes and daring space missions are about to probe the deepest mysteries of the cosmos. This journey will take you to the forefront of that exploration, revealing the most profound puzzles scientists are racing to solve in the coming year. You will gain a front-row seat to the investigations that could fundamentally reshape our understanding of reality itself. We will confront the invisible forces tearing space apart and search for whispers of life on distant worlds. What do you believe is waiting for us in the dark? Our first and greatest cosmic puzzle is one we cannot see. It is the mystery of dark matter, an invisible substance that makes up roughly 27% of everything in existence. Think of the entire universe as a vast cosmic machine. We can see the moving parts, the stars and galaxies, but we cannot see the immense, hidden engine that holds it all together. That engine is dark matter. It does not emit, absorb, or reflect any light, making it completely transparent to our telescopes. We only know it is there because of its immense gravitational pull, a ghostly hand that guides the rotation of galaxies and bends the very fabric of space itself. For decades, this has been the ultimate cosmic detective story, a search for a suspect we know only by its fingerprints. The year 2026 could be the year we finally get a clear look at the suspect. On the ground, in a mine deep beneath the Black Hills of South Dakota, the LUX Zeppelin experiment continues its silent vigil. This is not a telescope, but an ultra-sensitive trap. It is a vat of liquid xenon, chilled to extreme temperatures, waiting in profound darkness for a single, unimaginably rare event: the gentle bump of a dark matter particle passing through. Catching that signal would be a discovery for the ages, proving these elusive particles are real and tangible. Meanwhile, high in the Chilean Andes, a new eye on the sky is preparing to open. The Vera C. Rubin Observatory will soon begin its legacy survey of space and time, a 10-year project that will map the entire southern sky in breathtaking detail night after night. It will not see dark matter directly, but it will see its shadow. By observing how the light from billions of distant galaxies is warped by invisible mass, the survey will create the most precise map of dark matter's cosmic web ever made, showing us where this hidden scaffolding truly lies. Why does this matter so profoundly? Because dark matter is not just a missing piece of the universe, it is the foundation. Our entire understanding of how galaxies form, how the cosmos evolved after the Big Bang, and even the ultimate fate of the universe rests on knowing what this substance truly is. Is it a sea of exotic, undiscovered particles, as most physicists believe? Or could it be a sign that our laws of gravity, the rules written by Einstein, need a radical rewrite on the largest scales? The answer will not just fill a blank in a textbook, it will determine which path our understanding of reality takes for the next century. The search is closing in, and the clues we gather in 2026 may finally point us toward the truth. But the hunt does not end on the ground. It continues in the pristine silence of space, where a new generation of observatories is preparing to see the unseen in a way we never have before. Two spacecraft, the Euclid telescope from Europe and the upcoming Nancy Grace Roman Space Telescope from NASA, are embarking on a monumental task. They will not look for dark matter's particles, but for its shadow on the grandest scale imaginable. Their primary tool is a phenomenon called weak gravitational lensing. Think of it this way: imagine space as a vast, flexible sheet of rubber. A massive object like a cluster of galaxies sits on that sheet, creating a deep dimple. Now picture a beam of light from a galaxy far behind that cluster traveling toward you. As the light passes near the dimple, its path is bent, just like a marble would curve rolling past a depression. That bending distorts the image of the background galaxy, stretching it into a faint arc or smear. This is gravitational lensing in action. Now, dark matter creates its own invisible dimples in the fabric of space. While a single distortion is too subtle to see, by meticulously measuring the shapes of billions of distant galaxies, Euclid and Roman can detect the collective warping caused by all the dark matter lying between those galaxies and us. It is like mapping the contours of an invisible mountain range by watching how the wind flows over it. These missions will compile data of unprecedented scale and precision, weaving together the most detailed three-dimensional map of the dark matter cosmic web ever created. We will see its filaments connecting galaxy clusters and its vast, empty voids with stunning clarity. Yet the true revelation may lie in the anomalies. The exact way this cosmic web is woven, the thickness of its strands and the size of its holes, depends intimately on the properties of the dark matter particles themselves. Are they cold and slow-moving, allowing them to clump easily into small structures? Or are they warm and faster, smoothing out the small-scale details of the web? The maps from Euclid and Roman will hold the answer. If the maps reveal a web finer and more intricate than our models predict, it would point towards specific types of cold dark matter. If the web appears more diffuse, it could be evidence for warmer, more elusive particles. This is where the potential for a true paradigm shift emerges. What if, after all this searching and mapping, the dark matter web looks nothing like our best theories say it should? What if the expected signatures are simply not there? Such a result would be even more revolutionary than a confirmation. It would force us to question the very bedrock of modern cosmology, to consider that gravity itself might behave differently across cosmic distances, or that we are missing a fundamental ingredient in the recipe of the universe. The data flowing in through 2026 and beyond will not just fill in a map, it will test the limits of our understanding, pushing us toward either a triumphant discovery or a humbling, and perhaps even more exciting, rewrite of the rules. Yet for all its power, dark matter is not the universe's dominant force. That title belongs to something even more strange and elusive, a mystery that makes dark matter seem almost familiar by comparison. This is the enigma of dark energy. If dark matter is the hidden glue holding galaxies together, dark energy is the phantom force tearing the very fabric of space itself apart. It constitutes roughly 68% of everything in the cosmos, a vast, repulsive energy infused within empty space that is causing the expansion of the universe to accelerate. Think of the Big Bang as a mighty explosion, sending galaxies flying outward like shrapnel. For billions of years, scientists expected the mutual gravitational pull of all that matter to gradually slow that expansion, like gravity tugging on a ball thrown upward. But in the late 1990s, observations of distant supernova revealed something shocking. The expansion is not slowing down, it is speeding up. Something is actively pushing galaxies away from each other faster and faster over time. That something is dark energy. It is not a particle or a substance we can ever hope to touch. It appears to be a property of space itself, a kind of anti-gravity woven into the vacuum. The year 2026 promises crucial new data in our attempt to understand this bizarre force. The key lies in measuring the history of the universe's expansion with a precision once thought impossible. Enter the Dark Energy Spectroscopic Instrument, or DESI. Mounted on a telescope in Arizona, DESI is not taking pretty pictures of the cosmos. Instead, it is performing a massive cosmic census. It collects the light from millions of galaxies and quasars, splitting that light into detailed spectra, the unique chemical fingerprints that reveal not just what a galaxy is made of, but how fast it is moving away from us. By mapping the positions and velocities of over 30 million galaxies across 11 billion years of cosmic history, DESI is constructing a three-dimensional chart of the universe's growth unlike any before. It is measuring the subtle imprint of sound waves that rippled through the primordial universe, frozen into the large-scale structure of galaxies, acting as a standard ruler to gauge cosmic distances across time. Each data point from Daisy is a measurement of how fast space was stretching at a specific moment in the deep past. When combined with upcoming observations from facilities like the Simons Observatory in Chile's high Atacama Desert, which will map the faint afterglow of the Big Bang with unprecedented sensitivity, we will have two independent, ultra-precise records of the universe's expansion. Why is this so revolutionary? Because it will test the simplest and most profound idea about dark energy, that it is a constant force, unchanging throughout time and space, what Einstein once called the cosmological constant. But what if it is not constant? What if the strength of dark energy has been subtly changing over the billions of years since the Big Bang? The data from Daisy and the Simons Observatory are sensitive enough to detect such a drift. If they find even a tiny variation, it would shatter the cosmological constant model. A dynamic dark energy would mean the repulsive force of the vacuum evolves, perhaps growing stronger or weaker, completely altering the predicted fate of the cosmos. Instead of a future where galaxies fade into isolated darkness, we could be facing a far more dramatic end, a big rip where the fabric of spacetime itself is torn apart, or a reversal into a cosmic collapse. The results arriving through 2026 will tell us if the force dominating our universe is a steady whisper or a voice that changes its tone, deciding between a known, if lonely, future and a cosmic destiny we have not yet dared to imagine. While dark energy shapes the fate of the cosmos, another question burns even closer to the human heart. Are we alone? The search for an answer is moving from philosophy into forensic science, focusing on a new generation of worlds beyond our solar system. The next great leap hinges not on finding little green men, but on detecting subtle chemical whispers in the light of distant suns. These whispers are called biosignatures, and the hunt for them is entering a decisive phase. A biosignature is not a direct signal from an alien civilization. It is a clue written in the chemistry of a planet's atmosphere, a persistent imbalance that on Earth is maintained solely by life. The classic example is the simultaneous presence of oxygen and methane. In a lifeless, stable atmosphere, these two gases react quickly and destroy each other. Their enduring coexistence in our air is a billboard for biology, a product of plants pumping out oxygen and microbes releasing methane. Finding that specific combination on a distant world would be the most compelling hint of life we could hope to detect from light years away. The tools for this delicate task are now coming online. The James Webb Space Telescope has already begun analyzing the atmospheres of some larger exoplanets, and by 2026, its mission will be in full swing, refining its techniques on gas giants and Neptune-sized worlds. But the true revolution for Earth-like planets awaits the next flagship observatory. On the horizon is the Habitable Worlds Observatory, a mission designed with one primary goal: to directly image and analyze the atmospheres of at least 25 rocky planets orbiting in the habitable zones of their stars. This is not an easy task. It requires a telescope so stable and its optics so precise that it can block out the blinding glare of a host star, millions of times brighter than the tiny, pale blue dot orbiting it, to capture the faint spectral fingerprint of the planet's air. The potential targets for this search are already known, and they fire the imagination. There is the TRAPPIST-1 system, a compact family of 7 rocky worlds orbiting a cool, red dwarf star 39 light-years away. 3 of these planets sit squarely in the star's habitable zone, where temperatures could allow for liquid water on their surfaces. Then there is Proxima Centauri b, our nearest exoplanetary neighbor, a rocky world just over 4 light-years away, also orbiting in the temperate zone of its faint star. Analyzing the thin veil of atmosphere around such a world, if it has one, would be a historic first, yet the path to discovery is fraught with complexity. A biosignature must be unmistakable. Scientists face the daunting challenge of false positives, where geological or chemical processes mimic the signs of life. For instance, a planet with vast amounts of liquid water and ultraviolet light from its star can produce oxygen through simple photochemistry, no biology required. A world with intense volcanic activity could fill its air with methane. The key will be in the context, the full chemical story told by the atmosphere. Is there just oxygen, or is it paired with gases like methane or nitrous oxide in proportions that defy non-living explanations? Does the spectrum show signs of water vapor and a temperate climate, or is the planet a scorching, airless rock? The observations planned for 2026 and the years that follow will move us from simply detecting atmospheres to reading their complex narratives, searching for that rare, coherent story that points toward a living world. It is a painstaking process of elimination, where each new datum brings us closer to answering the oldest question of all. But the chemical whisper of a microbe is not the only signature we seek. Beyond the search for biological footprints lies an even more profound quest, the hunt for intelligence itself. This is the domain of technosignatures, the search for evidence not of life but of technology and civilization. While biosignatures look for the byproducts of metabolism, technosignatures look for the artifacts of a mind. They could be a powerful, narrowband radio signal deliberately beamed across the galaxy, the distinctive infrared glow of a vast megastructure capturing a star's energy, or even the spectral signature of artificial chemicals polluting an exoplanet's atmosphere. In 2026, this search is becoming more sophisticated and systematic than ever before. Leading the charge are projects like Breakthrough Listen, the most comprehensive search for extraterrestrial intelligence ever undertaken. This initiative uses some of the world's most powerful radio telescopes, like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to scan over 1 million of the nearest stars, as well as the center of our own galaxy and entire nearby galaxies. But it is not just about listening to more of the sky, it is about listening smarter. New machine learning algorithms are being trained to sift through the immense cosmic static, identifying unusual patterns that might be missed by human eyes, patterns that could be the faint, structured signal of a distant transmitter. Alongside the radio search, astronomers are also scanning the heavens in infrared light, looking for the telltale heat signature of hypothetical Dyson spheres. The idea, proposed by physicist Freeman Dyson, imagines an advanced civilization constructing a vast swarm of energy collectors around its star to harness its total power output. Such a megastructure would block the star's visible light but radiate waste heat in the infrared, appearing as a strangely warm object in the cold of space. Surveys from telescopes like NAS, a wide-field infrared survey explorer, have already flagged a handful of mysterious objects with unusual infrared profiles, and future observations will scrutinize these anomalies with intense focus. Yet the search for intelligence is not only directed at the stars, it has also turned its gaze inward toward visitors from beyond our solar system. The passage of the first known interstellar objects, Oumuamua in 2017 and Comet Borisov in 2019, opened a thrilling new frontier. While their natural origins are the most likely explanation, their unprecedented nature demands rigorous study. Future missions are being proposed to intercept the next such visitor, to study its composition and structure up close. Could a future interstellar object reveal signs of artificial construction, perhaps an unusually reflective surface, a peculiar shape, or even a non-gravitational acceleration not explained by simple outgassing? The scientific protocol is clear: to investigate without presumption, but the very possibility adds a tangible, urgent dimension to the search. This modern effort stands on the shoulders of a tantalizing historical mystery, the famous WOW. Signal. In August 1977, a radio telescope at Ohio State University detected a powerful, narrowband signal from the direction of the constellation Sagittarius that lasted for 72 seconds. It matched the expected profile of an artificial interstellar signal so perfectly that the astronomer who found it circled the computer printout and wrote, "Wow." Next to the data, despite decades of follow-up, the signal was never heard again. Today, with vastly more sensitive equipment and continuous monitoring of the sky, researchers are not only looking for new signals but are also revisiting the coordinates of the WOW signal and other historical anomalies, hoping to catch a repeat transmission or find a previously unnoticed clue. The search for technosignatures is a gamble on a cosmic scale. It probes the most ambitious question of all: are there other minds looking back at us? A confirmed detection would instantly answer that we are not the universe's sole thinkers, reshaping our philosophy, our science, and our place in the cosmos. Yet even the continued silence as the search grows ever more powerful carries a profound message, telling us that intelligence, or at least the kind that builds beacons, might be rarer and more precious than we ever imagined. While we listen for the deliberate signals of intelligence, the universe is already screaming at us in a language we do not understand. These are the fast radio bursts, or FRB, perhaps the most bizarre and violent transient events in the cosmos. Imagine, for just a single millisecond, a flash of radio waves so powerful it outshines an entire galaxy. That energy, concentrated into a blink of time shorter than a camera's shutter click, travels across billions of light-years of space to finally wash over our telescopes as a fleeting chirp in the data. Since their discovery in 2007, these bursts have been the ultimate cosmic flash mob, appearing without warning from random points in the sky and then vanishing, leaving behind only a profound mystery. What natural engine could possibly generate such staggering power in such an impossibly short time? The leading suspect is a magnetar, the crushed, hypermagnetic corpse of a massive star. A neutron star with a magnetic field 1,000 trillion times stronger than Earth's could, in theory, produce cataclysmic starquakes or magnetic flares capable of launching these intense radio pulses across the universe. Some FRBs are one-off events, a single, spectacular bang. Others are repeaters, firing off multiple bursts from the same patch of sky, which rules out any theory involving a one-time destruction like a star collapsing into a black hole. This repeating behavior points toward a source that can survive its own outburst, like a spinning, magnetic powerhouse. But the mystery deepens with the detection of an FRB from within our own galactic neighborhood, originating from a known magnetar in the Milky Way. This was a crucial clue, seemingly confirming the leading theory. Yet, the vast majority of FRBs come from far beyond our galaxy, from distances so immense their signals have been stretched and scattered by the tenuous gas between galaxies. Their sheer power at such distances challenges even the magnetar model, pushing the limits of physics. Could some be the birth cries of new black holes or the result of cosmic strings, theoretical defects in spacetime itself? Or, in a more speculative vein, could they be the signatures of unimaginably advanced technology, like power beams for interstellar light sails? The year 2026 marks a turning point in this detective story, because we are about to stop just hearing the screams and start finding exactly where they are coming from. A new generation of radio eyes is opening on the world. In Canada, the CHIME telescope, already a prolific FRB hunter, is being upgraded to see the sky with even greater clarity and precision. Its unique design allows it to scan the entire northern sky each day, making it an unparalleled trap for catching these fleeting events. But the true game changer is taking shape across 2 continents. The Square Kilometre Array, or SCAR, is beginning its construction in the remote deserts of South Africa and Western Australia. This is not a single telescope, but a vast network of thousands of radio antennas working in concert, creating a collecting area of, as the name suggests, approximately 1 square kilometer. When its initial Pathfinder arrays come fully online, their sensitivity will be staggering. They will not only detect thousands more FRBs, they will localize them with pinpoint accuracy. Currently, tracing an FRB to its host galaxy is a painstaking challenge, often requiring follow-up observations from other telescopes. The SKA's sheer power will allow it to do this in real time. When a burst chirps across its antennas, the array will instantly triangulate its position with such precision that optical telescopes can swing to that exact spot in the sky and see the galaxy it called home. This is the critical step. By firmly placing FRBs within specific types of galaxies, we can read their context. Do they always come from regions of frantic star formation where magnetars are likely being born? Or do they originate from calm, elderly galaxies, suggesting a different, slower process? Each localized burst adds a piece to the puzzle, narrowing down the list of possible culprits. With thousands of new events catalogued and their cosmic addresses known, patterns will emerge that are invisible today. We may find that one-off bursts and repeating bursts come from entirely different environments, pointing to two distinct cosmic phenomena. The data flowing in from these new telescopes will transform fast radio bursts from tantalizing anomalies into a new class of astronomical standard candle, a tool to probe the invisible matter strewn between galaxies. More importantly, it will finally reveal the engines behind these millisecond marvels, showing us whether they are the death throes of stars, the spin of magnetic cinders, or something even stranger, a fundamental process in the cosmos we have not yet dared to dream of. But the universe's most violent whispers are not the only ones that can shatter our understanding of matter. To find the ultimate limits of physical law, we must look to the silent, spinning tombstones left behind by supernova. These are neutron stars, the universe's most extreme laboratories. When a massive star dies in a cataclysmic explosion, its core collapses under unimaginable gravity. Electrons are slammed into protons, and everything fuses into a seething ball of neutrons. The result is an object of almost incomprehensible density. A single sugar cube-sized piece of a neutron star would weigh more than all of humanity combined, a mountain crushed into a teaspoon. These city-sized spheres spin hundreds of times per second. Their surfaces are polished smoother than a mirror by gravity, 100 billion times stronger than Earth's, and their magnetic fields could erase the data on every credit card on our planet from halfway across the Milky Way. Yet for all we know about their terrifying exteriors, their deepest secret lies within. What happens to matter when it is squeezed by pressures that make the core of an atomic bomb seem gentle? What is the true nature of the heart of a neutron star? The year 2026 will see a dedicated space mission and a new era on the cosmos work in concert to answer that. On the International Space Station, an instrument called the Neutron Star Interior Composition Explorer, or NISA, is already at work. NISA is not a traditional telescope with a lens. It is an array of super-sensitive X-ray detectors, precisely timed like the world's most accurate stopwatch. Its target is the steady pulse of radiation from rapidly spinning neutron stars known as pulsars. As these cosmic lighthouses rotate, their beams of X-rays sweep past NISA. By measuring tiny, rhythmic variations in the arrival time of these X-rays, scientists can perform an astonishing feat of cosmic cartography. They are mapping the size and shape of the neutron star itself. A larger star will have a different pattern of X-ray pulses than a smaller, denser one. This is like determining the exact dimensions of a distant, spinning marble by the precise flicker of its glow. But size is only half the story. To understand what is inside, we must also listen. This is where gravitational wave astronomy enters its next chapter. When a neutron star experiences a sudden crack in its crust, a starquake, it rings like a bell. That ringing distorts spacetime itself, sending out faint ripples that the next generation of observatories, like the planned Cosmic Explorer and the Einstein telescope, hope to detect. The frequency of that ring, the gravitational wave tone, reveals the internal stiffness of the star, telling us how its unimaginably dense matter responds to stress. By combining nicer precise size measurements with the future tones of starquakes, physicists will finally have the data to test what exists in that crushing core. Is it a superfluid sea of neutrons all the way down? Or does the pressure become so extreme that the neutrons themselves break apart into their constituent parts, a soup of free quarks and gluons, a state of matter not seen since the first microseconds after the Big Bang? There is an even more exotic possibility that strange particles called hyperons, which cannot exist under normal conditions, form in the core. Each possibility predicts a different relationship between a neutron star's size and its squishiness. The data arriving now is the key that will unlock which door is real. This quest is about more than cataloging cosmic oddities. It is a direct test of the fundamental forces that govern all matter, under conditions so extreme they can never be recreated in any laboratory on Earth. By deciphering the heart of a neutron star, we are reading the universe's own manual for how reality behaves at its absolute limit. Yet for all their destructive power, black holes are not just cosmic vacuums. They are also cosmic engines, and the very largest of them hold a secret about the dawn of time. At the heart of nearly every galaxy, including our own Milky Way, sits a supermassive black hole, a gravitational monster weighing millions or even billions of times our sun's mass. Their existence is a given, but their origin is one of the great outstanding puzzles of cosmology. How did these behemoths get so big so fast? The James Webb Space Telescope is now turning its infrared gaze to the earliest epochs of the universe, and what it finds may finally solve this ancient riddle. The problem is one of cosmic timing. We see fully formed supermassive black holes shining as brilliant quasars in galaxies that existed when the universe was less than 1 billion years old. That is not enough time for a typical stellar mass black hole, formed from a dying star, to grow to such a staggering size through mergers and by eating gas. It would be like finding a 200-year-old oak tree in a forest that is only 10 years old. The seed must have been enormous from the very beginning. So what planted those seeds? Astronomers have two leading and competing theories. The first is the direct collapse model. In this scenario, the first generation of stars were not like our Sun. They were colossal, perhaps hundreds of times more massive, and made almost entirely of hydrogen and helium. When such a star died, it would not go gently. It would collapse directly into a black hole with a starting weight of tens of thousands of solar masses, a giant seed ready to feast on the surrounding gas and grow rapidly. The second theory skips the star entirely. It proposes that in the ultra-dense early universe, vast clouds of primordial gas could have collapsed under their own gravity so violently and swiftly that they bypassed star formation altogether, crumpling directly into a massive black hole seed. The James Webb Space Telescope is uniquely equipped to test these ideas. Its powerful infrared vision allows it to peer through cosmic dust and see the light from the first galaxies and quasars as it was emitted over 13 billion years ago. In 2026, it will be conducting deep surveys specifically hunting for these infant monsters. Scientists are not looking for the black holes themselves, but for their fingerprints on their surroundings. A young, voracious black hole seed greedily pulling in gas would create a specific and furious signature of light. Webb can analyze the spectra of the earliest quasars, looking for clues about their mass and their diet, which in turn reveals their origin story. Did they grow from a single, massive collapse, or are they the product of a frantic, chaotic merger of many smaller black holes in a crowded galactic core? The answer is not just about the black holes, it is about the galaxies they live in. We now know that supermassive black holes and their host galaxies grow together in a tight, symbiotic dance. The energy blasting from a feeding black hole can heat up gas, stifling star formation, or it can trigger new waves of stellar birth. The initial conditions of the black hole seed, its size and its location, set the rules for that entire dance. Understanding which seed planting theory is correct will tell us how the first galaxies assembled themselves, why they look the way they do, and ultimately how a structure like our own Milky Way came to be. The data returning from the edge of time will decide between two very different visions of cosmic dawn, one lit by the death of the universe's first titanic stars, and another born from the silent, direct collapse of primordial clouds into the darkest seeds of all. The deepest mystery of a black hole is not what it consumes, but what it might erase. This is the black hole information paradox, a conflict at the very heart of physics that threatens to rewrite our understanding of reality. The problem begins with a startling prediction from Stephen Hawking. He calculated that black holes are not truly eternal. Through subtle quantum effects at their very edges, they slowly leak radiation and lose mass, evaporating over unimaginable timescales. This Hawking radiation, however, appears to be completely random, a featureless thermal fuzz. According to the unbreakable laws of quantum mechanics, information about the universe can never be truly destroyed. If you burn a book, its ashes and smoke still contain, in principle, the information needed to reconstruct every word. But Hawking's math suggested that if you throw that same book into a black hole, and the black hole later evaporates away, all the information about that book, the story, the characters, the very fact it was a book would be permanently lost, leaving behind only that bland hum of radiation. It would be as if the universe itself forgot. This posed an impossible choice. Either Hawking was wrong and black holes do not evaporate, or quantum mechanics, the flawless rulebook for the subatomic world, is fundamentally incomplete. The year 2026 brings us powerful new tools to probe this paradox. The Event Horizon Telescope collaboration, which gave us the first breathtaking images of the black holes M87 star and Sagittarius A star, is not done. Its next phase involves analyzing not just the silhouette of these monsters, but the incredibly complex dynamic swirl of light and magnetic fields around them. By watching how matter churns and energy flares at the very precipice of the event horizon, scientists hope to find subtle signatures of processes that might preserve information. One radical idea is holography, the notion that all the information about what falls into a three-dimensional black hole is not lost inside, but is instead smeared like a cosmic code onto its two-dimensional surface, the event horizon. The turbulent data from the Event Horizon Telescope could reveal patterns in the plasma around the black hole that serve as echoes of this encoded information, like seeing the ripples from a stone thrown into a pond long after the stone has sunk. Meanwhile, theorists are wrestling with another potential clue, the firewall paradox. This idea suggests that to preserve information, the event horizon might not be the smooth gateway predicted by Einstein's relativity. Instead, it could be a searing wall of high-energy particles, a literal firewall that would incinerate anything crossing it. While this solves the information problem, it creates another by violating the principle that falling into a large black hole should be uneventful at first. Resolving this requires a theory of quantum gravity, a framework that can marry the cosmic rules of general relativity with the tiny rules of quantum mechanics. Remarkably, we may not need to look to the stars to test these ideas. In laboratories around the world, physicists are creating analog black holes using supercooled fluids or carefully arranged lasers. In these controlled setups, they can simulate an event horizon and study the analog of Hawking radiation in a tabletop experiment. By tweaking these analog systems, they can explore how information might escape or be preserved, offering tangible clues from the safety of a lab. The breakthroughs we seek in 2026, whether from the edge of a real black hole or a simulated one in a crystal, are not just about solving a theoretical puzzle. They are about discovering the missing link that unifies the two great pillars of modern physics, finally revealing how the universe preserves its memory in the face of oblivion. The final fate of the cosmos hinges on a single critical number. This is the Hubble constant, the rate at which the universe is expanding at this very moment. It is the master dial that sets the timeline for everything that ever was or will be. And right now, we have two very precise yet stubbornly different measurements for what that number should be. This discrepancy is the Hubble tension, and it is the single most pressing problem in cosmology today. One method looks back to the dawn of time, using the ancient afterglow of the Big Bang, the cosmic microwave background, as a perfect snapshot of the infant universe. By measuring tiny ripples in that light, we can calculate how fast the universe should be expanding today. Another method looks at the relatively recent universe, using stellar explosions called Type Ia supernova and pulsating stars called Cepheid variables as cosmic mile markers. By measuring their distances and how fast they are receding, we get a direct read on the current expansion rate. Both methods are exquisitely precise, but they do not agree. They are off by a small but significant amount. It is as if two of the world's most accurate clocks, built on different principles, are ticking at undeniably different speeds. This is not a minor accounting error. It is a potential crack in the foundation of our standard model of the universe. The year 2026 will see a flood of new data aimed squarely at resolving this tension. The James Webb Space Telescope is now meticulously observing Cepheid variables and supernova with a clarity far beyond Hubble's, checking for any hidden systematic errors in our local measurements. At the same time, ground-based observatories like the Simons Observatory are preparing to map the cosmic microwave background with 50 times the sensitivity of previous missions, scrutinizing the early universe data for any subtle flaw. The goal is not to prove one side right, but to see if the discrepancy holds under this unprecedented scrutiny. If, after all this, the tension remains, it would be a monumental discovery. It would mean our standard cosmological model, the lambda-cold dark matter model that has guided us for decades, is incomplete. We would need new physics. Perhaps dark energy is not constant but evolving, growing stronger over time. Maybe there is an unknown type of neutrino or another exotic particle from the early universe subtly changing the expansion history. Or perhaps the fabric of spacetime itself has properties we have not yet accounted for. This is why the Hubble tension is so vital. It is our best clue that we are on the verge of a deeper understanding. The resolution of this tension will not just give us a number, it will point us toward the universe's ultimate destiny. Currently, the leading forecast is the Big Freeze or heat death. In this scenario, dark energy remains constant, driving galaxies apart forever. Star formation will eventually cease, black holes will evaporate over eons, and the cosmos will become a cold, dark, and dilute sea of fundamental particles, a state of maximum entropy where nothing ever happens again. But if new data suggests dark energy is dynamic and growing in strength, a far more dramatic ending comes into view: the Big Rip. In this fate, the repulsive force of dark energy would overcome all other forces in the universe, not just pushing galaxies apart, but tearing apart galaxies themselves, then solar systems, planets, and finally the very atoms that make up matter, shredding the fabric of spacetime in a final, catastrophic instant. There is also a third, more cyclical possibility: the Big Crunch. This would require dark energy to weaken or reverse, allowing gravity to finally halt and reverse the expansion. The universe would collapse back in on itself, potentially leading to another Big Bang in an endless cycle of cosmic rebirth. The data we gather in the coming years, especially the precise measurements of the Hubble constant, will tilt the scales toward one of these profound endings. We are not just measuring expansion, we are reading the first chapter of the universe's final story. The Hubble tension reveals a universe whose rulebook may have missing pages, but some of the most startling clues are not written in ancient light. They are physical objects passing through our own cosmic neighborhood. The door to interstellar visitation was opened in 2017, and it left us with more questions than answers. That year, astronomers in Hawaii spotted a faint, fast-moving point of light tracing a path that could only mean one thing: it was not from here. Named Oumuamua, Hawaiian for scout or messenger from afar, it was the first confirmed object from another star system to pass through our solar system. Its discovery was a landmark, but its characteristics were baffling. Based on the way its brightness changed dramatically as it tumbled, its shape appeared to be highly elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a pancake. Even stranger was its motion. As it sped away from the sun, it exhibited a slight but definite extra push, a non-gravitational acceleration that could not be explained by the sun's gravity alone. Comets often show such pushes when their icy surfaces heat up and vent gas, creating a jet-like effect. Yet Oumuamua showed no visible coma, the cloud of gas and dust that surrounds a comet's nucleus. This left scientists in a heated debate. Was it a rocky asteroid shaped by extraordinary forces, a comet with a very unusual composition that released gas without visible dust, or something even more exotic? The data was gone as quickly as the object, leaving only speculation in its wake. The anticipation now is not for a repeat, but for a revolution in our understanding. The era of the lone interstellar scout is about to end, replaced by an age of interstellar crowds. The Vera C. Rubin Observatory's legacy survey of space and time will begin its relentless scan of the sky, and its powerful, wide-eyed gaze is expected to detect not just one, but potentially several interstellar visitors every single year. This will transform these objects from rare curiosities into a new population for statistical study. We will learn their typical shapes, their colors, their orbits. Are most like Oumuamua, or like the more conventional interstellar comet Borisov that followed in 2019? This flood of data will begin to tell us what is normal out there in the galaxy. But statistics are one thing, touching is another. The ultimate goal, actively taking shape in mission design labs, is to not just watch the next visitor pass by, but to chase it down. Plans are being drawn for rapid response interceptor missions. The concept is to have a spacecraft, perhaps even a fleet of them, pre-built and ready on the launch pad, fueled and waiting for the alert. When the next interstellar object is detected on its inbound journey, telescopes would scramble to precisely calculate its trajectory. Then, within a very short window, a heavy-lift rocket like SpaceX's Starship could launch, using its immense payload capacity to carry a sophisticated suite of instruments on a high-speed rendezvous. Imagine catching up to this visitor as it swings through the inner solar system, flying alongside it to capture high-resolution images of its surface, analyzing its composition with spectrometers, and even attempting to sample particles from its vicinity or land a small probe. Such a mission would settle the debates about Oumuamua instantly. Is the surface dark and rocky, or icy and hidden? Does it outgas particular molecules? What created its strange shape, a colossal collision in its home system, or the slow erosion of cosmic rays over billions of years? The answers would be a direct sample of a planet-building system from around another star, a piece of another world delivered to our doorstep. The data would tell us about the chemistry and physics of systems light years away, offering a tangible check on our theories of how all planetary systems form and evolve. The next time an interstellar messenger arrives, we intend to be ready not just to see it, but to meet it, and finally understand what these silent travelers are telling us about the galaxy we all share. But to hear the universe's very first whisper, we must go to the one place in the inner solar system cloaked in perfect silence. This is the far side of the Moon, a location of profound and eerie quiet that holds the key to our cosmic origin story. While the Moon's familiar face is bathed in Earth's constant glow, its hidden hemisphere is permanently turned away from our planet's cacophony. It is shielded from the relentless radio chatter of our civilization, our television broadcasts, our satellite signals, and even the natural radio noise from our planet's magnetic field. This creates the most pristine radio-quiet environment for hundreds of thousands of miles, a silent sanctuary on a lifeless rock. It is here, in this absolute stillness, that scientists hope to tune into a signal from the dawn of time itself, from a period known as the Cosmic Dark Ages. This era is one of the last great uncharted chapters in the history of everything. It spans the time between two monumental events. First, the fading of the Big Bang's afterglow, the cosmic microwave background, about 380,000 years after the beginning. Then, hundreds of millions of years later, the ignition of the very first stars, ending the darkness. During this vast, silent epoch, the universe was a simple, cold, and dark place. It contained only a featureless sea of hydrogen and helium gas and the invisible scaffolding of dark matter. There were no stars, no galaxies, no sources of light. It was the universe's long, deep breath before the fireworks began. Yet that neutral hydrogen gas was not completely silent. It emitted a faint, specific radio signal at a wavelength of 21 centimeters. As the universe expanded, that signal has been stretched or redshifted into much longer, lower-frequency radio waves today. This is the signal we need to hear. It is a direct broadcast from the Dark Ages, a map of the universe when it was still smooth and pristine. Detecting this signal is arguably the hardest observation in all of astronomy. The whisper from the infant universe is incredibly faint, buried under a sea of radio noise thousands of times stronger from our own galaxy and the Earth itself. It is like trying to hear a single drop of rain fall in a roaring hurricane. This is why the lunar far side is not just an option, it is a necessity. Upcoming missions are now aiming to turn this silent landscape into the ultimate cosmic observatory. NASA, in partnership with the Department of Energy, is developing the Lunar Surface Electromagnetics Experiment, or LUC. This Pathfinder mission is designed to land on the far side and do one critical thing: survive. The environment is brutally hostile, with 2 week-long nights of deep cold and days of scorching heat. LUC's goal is to prove that sensitive radio astronomy equipment can operate there at all, taking the first tentative listen for that primordial signal. It is a technological scout paving the way for more ambitious projects. These future projects are visions of a new kind of astronomy. Concepts include deploying vast arrays of simple radio antennas across the lunar soil, or even building a giant telescope inside a crater, using the natural bowl shape as a perfect dish. International efforts like China's planned Chang missions could also contribute to this quiet revolution, potentially deploying their own radio astronomy instruments on the far side. The global scientific community recognizes this unique location as a shared opportunity to peer back to our universal beginnings. What could this ancient signal possibly tell us? Everything. A clean detection of the Dark Ages signal would be a time machine. By mapping its subtle variations, we could see how the hydrogen gas was distributed before the first stars stirred it up. We could watch how the invisible hand of dark matter began to pull that gas into the first proto-galaxies. We might even find imprints from the universe's most violent infancy, gravitational waves from the Big Bang itself, patterns frozen into that primordial hydrogen. It is a direct test of our entire cosmic timeline, from inflation to the first starlight. If the signal matches our predictions, it would be a triumphant validation of our standard model of cosmology. But if it deviates, if the ancient universe whispers a story we do not expect, it could point to new physics, to exotic properties of dark matter, or to energies at work in the cosmos's first moments that we have never dreamed of. The silent side of our nearest neighbor holds the key to the loudest questions of our existence. Yet to hear the universe's first whisper, we must leave the silent moon behind and journey outward to a pair of worlds that whisper their own much closer secrets. Uranus and Neptune, the ice giants, are the most distant and mysterious planets in our own solar system. They are not merely the last stops on a cosmic tour, they are profound enigmas, alien kingdoms of ice, gas, and storm that represent an entire class of planet we have barely begun to understand. For a fleeting moment in the late 1980s, we caught a glimpse. The Voyager 2 spacecraft raced past each of them, a pair of hurried flybys that gave us our only close-up portraits. Those images revealed worlds of astonishing beauty and bizarre behavior. Uranus tipped completely on its side, rolling around the sun like a celestial billiard ball. Neptune, a deep, brilliant blue, scarred by a giant dark storm and whipped by the fastest winds in the solar system. And then Voyager sped away into the void, leaving us with a handful of snapshots and a mountain of questions. For over 3 decades, we have been studying these planets from an immense distance, squinting at fuzzy dots through Earth's best telescopes, trying to decipher the secrets of their hidden hearts. We do not know what lies deep within them. Are they built around a solid, rocky core or something more exotic? Their magnetic fields are wildly off-kilter, not aligned with their poles, and they seem to originate from strange, slushy layers within the planets rather than a central dynamo. Their extreme seasons, each lasting decades, must drive weather systems unlike anything else we know, but we have only seen brief moments in those long cycles. The fundamental mystery is what they are made of and how they formed. The term ice giant is a bit misleading. It does not mean a giant ball of solid ice. Think of them instead as vast, fluid worlds with relatively small, dense cores enveloped by deep, superheated oceans. Not oceans of water as we know it, but a hot, dense, electrically conductive fluid mixture of water, ammonia, and methane under incredible pressure. This exotic ocean, thousands of miles deep, transitions into a thick atmosphere of hydrogen and helium. They are a hybrid, a missing link between the gas giants like Jupiter and Saturn and the rocky worlds like Earth. Understanding their precise recipe is crucial because it turns out ice giants may be the most common type of large planet in the galaxy. Among the thousands of exoplanets we have discovered, worlds the size of Uranus and Neptune appear everywhere. To truly grasp how planetary systems form and evolve across the cosmos, we must first understand the 2 archetypes we have in our own backyard. This is why the scientific call for a return has grown into a roar. The next great leap in planetary science is a dedicated orbiter mission to one of these distant worlds, with the current favorite target being Uranus. A mission concept, often called the Uranus Orbiter and Probe, represents a monumental undertaking. It would not be a flyby, it would be a commitment. After a journey lasting well over a decade, the spacecraft would arrive and break into orbit, becoming an artificial moon of Uranus for years of detailed study. It would map the planet's faint rings and diverse moons in exquisite detail, monitor its strange weather across seasons, and chart its lopsided magnetic field. The crowning achievement would be the release of an atmospheric probe, a bullet-shaped pod that would plunge into the blue-green haze, transmitting data on composition, temperature, and pressure as it descends, tasting the alien air directly until the immense pressure crushes it. The year 2026 could be the pivotal moment when this vision starts to become steel and silicon. It is a key decision point for space agencies like NASA and the European Space Agency as they set priorities for the next decade of flagship exploration. Scientific panels have already ranked an ice giant mission as a top priority for planetary science. A formal selection and the beginning of intense development in the coming years would set the stage for a launch in the early 2030s, with arrival at Uranus by the mid-2040s. The data it would eventually send back would rewrite textbooks. By analyzing the gravitational tug of the planet on the orbiter, we could finally map its internal structure, distinguishing between different models of its hidden core. Measurements from the probe would tell us exactly what that deep ocean is made of, revealing the balance of water, ammonia, and other molecules that were present in the outer solar system when the planets formed. This is a forensic investigation into the birth of our solar system. The ice giants are thought to have formed farther from the Sun than Jupiter and Saturn, in a region where icy building blocks were abundant. Something, perhaps a gravitational dance with the giant planets, then scattered them outward to their current orbits. Studying Uranus up close is like examining a preserved relic from that ancient, chaotic construction zone. Every measurement is a clue to the forces that shape not just our solar system, but countless others. To unlock the mystery of the most common large planets in the universe, we must first learn to read the two cryptic worlds at the edge of our own celestial neighborhood. The quest for life does not require us to travel to distant stars. Some of the most promising habitats in the entire cosmos are right here in our own solar system, hidden beneath the frozen crusts of alien moons. These are the ocean worlds, and they have transformed our understanding of where life could exist. The old rule was simple: life needs a planet orbiting in the Goldilocks zone, not too hot and not too cold from its sun. But the discovery of vast, salty, subsurface oceans on moons orbiting the gas giants Jupiter and Saturn shattered that rule. These moons are heated not by sunlight, but by the immense gravitational tug of war with their giant parent planets. This tidal friction keeps their interiors warm enough to maintain liquid water oceans, in some cases containing more water than all of Earth's oceans combined, sealed beneath a shell of ice. The three most compelling of these worlds are Europa, Enceladus, and Titan, and each presents a unique and tantalizing mystery. Europa, a smooth, cracked marble orbiting Jupiter, has long been the prime candidate. Its surface is a labyrinth of crisscrossing reddish-brown ridges and fractures, a clear sign of a geologically active ice shell floating atop a global ocean. The mystery is not if Europa has an ocean, but what is in it. How deep does it go? Is the seafloor rocky and heated by hydrothermal vents, environments that on Earth are teeming with life independent of the Sun? The Europa Clipper mission, launched in 2024, is now on its long journey to answer these questions. By 2026, the spacecraft will be in the quiet cruise phase of its interplanetary trek, but the work is just beginning. Engineers will be performing crucial checkouts of its sophisticated suite of 9 instruments, ensuring every radar system, every spectrometer, and every camera is ready for the moment of truth. They will also be refining its complex orbital dance at Jupiter, a series of nearly 50 flybys designed to map the moon's ice shell, measure the ocean's depth and salinity, and even sample the tenuous atmosphere for signs of material being vented from below. Clipper will not land, but its data will tell us if Europa's hidden sea has the right chemistry and energy to be a cradle for life. At Saturn, the small moon Enceladus has already shouted its secrets into the void. The Cassini spacecraft witnessed something astonishing: gigantic geysers of water vapor and ice erupting from a series of warm fractures near the moon's south pole. These plumes blast hundreds of miles into space, creating one of Saturn's iconic rings. Cassini even flew directly through these plumes, tasting them with its instruments. It found they were salty, contained organic molecules like methane and propane, and had tiny grains of silica that strongly suggest hydrothermal activity on the seafloor where hot water meets rock. The mystery of Enceladus is now one of specifics. What is the exact composition of those complex organics? Are there signs of amino acids or other building blocks of life? The plumes are a free sample delivered from the ocean to any passing spacecraft. Future missions, concepts being studied right now, aim to return to Enceladus with more advanced analyzers, perhaps even a lander that could sample the fresh ice falling back to the surface near the tiger stripe fractures. Each new piece of data from this tiny, active world makes it a more compelling target in the search for extraterrestrial biology. Then there is Titan, Saturn's largest moon, a world so utterly alien it feels like science fiction. Titan is shrouded in a thick orange haze, has rivers and lakes of liquid methane and ethane on its surface, and has mountains of water ice as hard as rock. Beneath this bizarre, hydrocarbon-rich surface, however, evidence suggests Titan, too, harbors a subsurface ocean of liquid water. But Titan's true mystery is not just about a hidden ocean, it is about the complex probiotic chemistry happening in plain sight on its surface. In the cold methane rivers and under its hazy skies, the very chemical processes that might have led to life on Earth billions of years ago could be playing out right now, but with a completely different set of ingredients. This is why NASA's Dragonfly mission is so revolutionary. Currently in advanced development, Dragonfly is not a rover, it is a dual quadcopter drone. By 2026, this audacious mission will be moving from design into the construction and testing of its actual flight systems. Scheduled to launch in 2028, Dragonfly will land on Titan in the mid-2030s, then take flight. It will hop from one site of interest to another, sampling the organic rich sands of Titan's dunes and even landing in a dry lake bed to investigate the chemical residues left behind. Its goal is to understand how far complex organic chemistry can progress in an environment rich in carbon but devoid of liquid water on the surface. Is Titan a frozen snapshot of the steps that led to life on Earth? Or could its subsurface water ocean, interacting with the organics above, have taken a different path entirely? These three worlds represent our best and nearest chances to answer the question of whether we are alone. Europa offers a potentially Earth-like ocean environment. Enceladus provides direct, accessible samples of its ocean. Titan presents a laboratory for the chemistry of life under alien rules. The missions heading their way, Europa, Clipper, and Dragonfly, are not merely voyages of exploration. They are forensic investigations. They will analyze the chemical fingerprints, map the hidden structures, and search for the imbalances that shout biology. The data they begin to send back in the coming decade will not just tell us about moons, it will tell us about the fundamental habitability of the universe. Is life a cosmic imperative, sparking wherever the right conditions persist, even in the cold, dark depths of an outer solar system ocean? Or are these magnificent, watery worlds beautiful but silent? The journey to find out is already underway, and the clues are waiting beneath the ice. Mars holds a secret written in a whiff of gas. The story of Martian methane is a detective tale unfolding in real time, a puzzle where every clue seems to contradict the last. On Earth, methane in the air is a powerful biosignature, a gas largely produced by living organisms, from microbes in wetlands to the digestive systems of cattle. So when our robotic explorers on Mars began detecting traces of this same gas in the thin Martian atmosphere, it sent a jolt of excitement through the scientific community. The detections, however, have been maddeningly inconsistent. They appear in sudden, localized spikes, sometimes 10 times the background level, only to vanish completely within weeks or even days. This erratic behavior is the heart of the mystery. If the methane were coming from a steady, planet-wide geological source, we would expect to see a constant, low-level presence. Instead, we see fleeting puffs, as if something is occasionally opening a valve, releasing a burst of gas, and then sealing it shut again. The central question is simple yet profound: what is turning that valve on and off? There are two primary suspects, and they lead to vastly different conclusions about the nature of the red planet. The first suspect is geology. methane can be produced abiotically without any life involved through a process called serpentinization. This occurs when certain minerals like olivine, rich in iron and magnesium, react with water deep underground. The chemical reaction produces heat, alters the rock, and can release hydrogen gas, which can then combine with carbon to form methane. If this is happening on Mars, it would point to ongoing hydrothermal activity, a sign of a geologically warmer and wetter interior than we assumed, possibly with pockets of liquid water interacting with rock. The second suspect, of course, is biology. Subsurface microbial life, similar to methanogenic archaea on Earth that thrive in places devoid of oxygen, could be producing methane as a waste product. Such life would likely exist far below the harsh, irradiated surface, perhaps in deep aquifers or in the pores of rocks, sustained by chemical energy rather than sunlight. Each new spike of methane is a potential whisper from this hidden biosphere. By 2026, the investigation is moving from simple detection to forensic correlation. The ExoMars Trace Gas Orbiter, a European-led mission, continues to scan the Martian atmosphere with unprecedented sensitivity, mapping the global distribution of methane and other trace gases. Its data is crucial because it can see the big picture from orbit, identifying regional patterns. Meanwhile, on the ground, NAS, a Curiosity rover in Gale Crater, acts as our local detective, sniffing the air directly and recording these transient spikes with its sample analysis at Mars Instrument. The upcoming key is to connect these two perspectives. Scientists are meticulously trying to correlate the timing of Curiosity's ground-level methane spikes with the orbital data from the Trace Gas Orbiter. Did the orbiter see a plume over Gale Crater at the same time? Can the orbiter trace a plume back to its point of origin, perhaps a specific fracture, an ancient river delta, or a particular type of geological formation? Furthermore, researchers are looking for patterns linked to the Martian seasons, temperature changes, or even the time of day. Does methane spike more often at night when the atmosphere is calmer? Does it appear more frequently during the planet's warmer months when subsurface ice might melt and release trapped gas? The Perseverance rover, exploring the ancient river delta in Jezero Crater, adds another critical layer. While its primary mission is caching samples for future return to Earth, its instruments also monitor the atmosphere. If Perseverance, thousands of miles from Curiosity, also detects a methane spike at the same time, it would suggest a widespread source or a globally circulating event, changing the scale of the mystery entirely. The data gathered through this period aims to build a behavioral profile of the methane. Is it seeping out along geological fault lines, suggesting a subsurface reservoir? Is it being released from sun-warmed surface rocks that had trapped ancient gas, a non-biological explanation? Or do the release patterns hint at something more dynamic, more responsive to environmental conditions, a signature that might align with a biological process? Every datum narrows the possibilities. A confirmed link between methane releases and specific, water-altered mineral sites would powerfully support the geological hypothesis. Conversely, if the methane appears most strongly in regions with ancient clays or near potential subsurface water, and its release seems disconnected from simple surface heating, the biological explanation gains weight. This is not a mystery that will be solved with a single measurement. It is a painstaking process of elimination, building a statistical case, one frustrating, disappearing clue at a time. The answer, when it finally comes, will not arrive with a shout, but with a consistent pattern emerging from the noise, telling us whether the red planet is merely geologically interesting, or if it is, against all odds, subtly, quietly alive. Beyond the last known planets lies a silent, frozen graveyard of the solar system's infancy. This is the Kuiper Belt, a vast donut-shaped region stretching far past the orbit of Neptune, populated by countless icy worlds, some as large as small planets, most no bigger than cities. For decades, it was thought to be the final frontier, a quiet repository of primordial leftovers. But then astronomers began tracking the paths of the most distant known objects within it, and a profound anomaly emerged. A handful of these extreme Kuiper belt objects follow orbits that are strangely clustered. Their elongated paths around the Sun are tilted in a similar direction and grouped together in space in a way that defies easy explanation by the known gravity of the 8 planets alone. It is as if an unseen hand is herding them, keeping their orbits aligned. The most compelling explanation for this gravitational shepherding is a hidden planet, a world perhaps 5 to 10 times the mass of Earth, orbiting the Sun on a distant, tilted path far beyond the Kuiper belt. This hypothetical world has been called Planet 9, or historically Planet X. Finding it, however, is a monumental challenge. If it exists, Planet 9 would be incredibly faint, reflecting only the barest sliver of sunlight from its immense distance, and its orbit could take between 10 and 20,000 years to complete. Searching for it is like looking for a single, dim lighthouse on a coastline that stretches for light years, not knowing exactly where along that coast it might be. This is where a new era of discovery begins. The Vera C. Rubin Observatory, poised to begin its legacy survey of space and time, is the perfect tool for this cosmic hunt. Its enormous mirror and gigantic camera are designed to scan the entire southern sky every few nights with a depth and speed never before achieved. It will not look for Planet 9 directly, but will instead map the positions of billions of stars and galaxies, night after night for a decade. Within that flood of data will be the tiny, moving dots of countless distant solar system objects. By tracking their motions with exquisite precision, the survey will discover thousands of new Kuiper belt objects, dramatically expanding our census of this distant region. The power of this survey lies in its ability to test the Planet 9 hypothesis with definitive data. If the planet is there, its immense gravity will subtly influence the orbits of every new object the Rubin Observatory finds. By analyzing the orbits of these newly discovered distant bodies, astronomers will be able to perform a celestial calculation of unprecedented scale. They can essentially triangulate the position of the unseen shepherd by the precise alignment of its flock. The survey's relentless scanning means that if Planet 9 is within its field of view and above a certain brightness, it will almost certainly be detected, its slow motion against the background stars flagged by powerful software. Conversely, if the survey completes its deep scan of the southern sky and finds no sign of the planet, and if the orbits of the new Kuiper belt objects show no further anomalous clustering, it will powerfully suggest that Planet 9 does not exist in the form we have imagined. The mystery of the clustered orbits would then need a different solution, perhaps pointing to the collective gravity of many smaller objects, or even to a lingering effect from the solar system's chaotic formation. The implications of either outcome are profound. Discovering a true Planet 9 would be the first addition of a major planet to our solar system in over 170 years, rewriting our family portrait overnight. Its existence would tell a dramatic story about our system's violent youth, suggesting it was either captured from another star or violently ejected from the inner solar system long ago, only to be pinned in a distant orbit by the galaxy's tide. Its nature, whether a rocky super-Earth or a gaseous mini-Neptune, would reveal entirely new planetary formation processes in the cold outer reaches. Ruling it out, however, would be a different kind of breakthrough. It would force a radical rethinking of celestial mechanics in our own backyard, challenging us to find a new explanation for the orbital oddities that started this search. The answer, delivered by the cold, objective data of a machine scanning the night, will close one chapter of solar system exploration and immediately open another, proving that even our own cosmic neighborhood still holds epic secrets waiting in the dark. But our own star holds a mystery just as deep, a hidden engine of chaos that governs the very space around us. This is the Sun's magnetic heartbeat, a rhythm that defines life on Earth in ways we are only beginning to understand. Every 11 years, like clockwork, the Sun's magnetic field undergoes a dramatic reversal. Its north and south poles flip, and in the turbulent build-up to that moment, our star erupts into a period of ferocious activity known as the solar maximum. We are entering one right now, with the peak predicted for 2025 through 2026. This is not a distant astronomical event. It is a storm front heading directly for our technological civilization. During solar maximum, the Sun's face becomes marred by dark sunspots, regions of intense magnetic energy. These are the launch pads for solar flares, sudden explosions of radiation that travel at the speed of light, and coronal mass ejections, billion-ton clouds of magnetized plasma hurled into space at millions of miles per hour. When these storms are aimed at Earth, the consequences are both beautiful and dangerous. They paint our skies with shimmering auroras, but they also slam into our planet's magnetic field. The resulting geomagnetic storms can induce powerful electrical currents in the ground. These currents seek the path of least resistance, which often means our continent-spanning power grids and the vast networks of pipelines and railways buried beneath our feet. A direct hit from an extreme storm like the Carrington event of 1859 could trigger widespread, long-lasting power blackouts, disable satellites we rely on for communication and navigation, and even cripple the sensitive electronics in spacecraft and high-altitude aircraft. The modern world has never faced a solar superstorm of that magnitude, and our interconnected infrastructure is more vulnerable than ever. Yet within this danger lies an unprecedented scientific opportunity. For the first time in human history, we have frontline observers stationed to witness the solar maximum up close. The European Space Agency's Solar Orbiter and NASA's Parker Solar Probe are not just watching from a distance, they are diving into the inferno. Parker, the bravest of the two, is flying closer to the Sun than any spacecraft before, repeatedly plunging through the Sun's superheated outer atmosphere, the corona. Its mission is to touch the star, sampling the solar wind and magnetic fields at their source. Solar Orbiter takes a different approach, equipped with a suite of telescopes to image the Sun's poles for the first time, regions crucial to generating the global magnetic field that drives this 11-year cycle. Their coordinated observations during this peak of activity are a once-in-a-generation experiment. They aim to solve two of the Sun's most enduring puzzles. First, the coronal heating problem. The Sun's visible surface is about 10,000 degrees Fahrenheit, but the corona above it soars to millions of degrees. It is as if the air around a light bulb were thousands of times hotter than the bulb's glass. How does the Sun accomplish this? The leading theory points to the tangling and snapping of magnetic field lines, a process called magnetic reconnection, which can release colossal energy in tiny nanoflare explosions. Parker and Solar Orbiter are positioned to catch this process in the act. Second, they seek to understand the trigger for the Sun's most violent outbursts. What determines whether a tangled magnetic field will quietly relax or suddenly detonate, launching a coronal mass ejection toward the planets? By measuring the magnetic field and plasma conditions right before a flare erupts, these probes will give us the data to finally predict solar weather with the reliability we now have for terrestrial storms. The knowledge gained in the coming year is not just academic, it is the foundation for building a more resilient future. Understanding the Sun's tantrums is the first step toward shielding our satellites with better designs, hardening our power grids with smarter safeguards, and giving astronauts future warnings to seek shelter from radiation. We are learning to read the moods of our star, transforming a source of ancient fear into a force we can comprehend and prepare for. The faintest whisper from our own spacecraft can challenge the very laws of physics. Decades ago, as the Pioneer 10 and 11 probes sailed into the dark beyond Pluto, scientists noticed something deeply strange. The spacecraft was slowing down by a tiny, almost imperceptible amount, more than any known force could explain. This was the Pioneer anomaly, a minuscule deceleration that seemed to tug at the probes as they fled the solar system. After years of painstaking analysis, the leading explanation became a surprisingly mundane one: the gentle, uneven push of heat radiating from the spacecraft's own nuclear power sources. Yet, even with that answer, a whisper of doubt remains. Could there be something more, a subtle flaw in our understanding of gravity itself that only reveals itself in the profound emptiness of deep space? The year 2026 offers a new chance to listen for that whisper, using the solar system itself as the most precise laboratory we have ever built. The key lies in the silent ballet of our robotic ambassadors. Modern missions like the Voyager probes, now in interstellar space, and the distant New Horizons spacecraft are tracked with phenomenal accuracy. Their positions are known down to a matter of meters across billions of miles, measured by the precise timing of radio signals sent from giant antennas on Earth. Any deviation from their predicted paths, any tiny, unexpected nudge in their velocity, is a potential clue. As these spacecraft venture farther into the cold, dark reaches where the sun's gravity weakens to a faint whisper, they become exquisite tests of gravitational law. If an unexplained acceleration or deceleration like the Pioneer anomaly appears again, especially on a spacecraft designed to minimize thermal effects, it would reignite the mystery with undeniable force. This is not merely about navigation, it is about using the trajectories of human-built objects to probe the fabric of the cosmos. Such a discovery would lend startling credibility to a radical class of theories known as modified Newtonian dynamics, or MN. These theories propose a breathtaking idea that we do not need invisible dark matter to explain the universe. Instead, they suggest that our equations for gravity, Isaac Newton's and Albert Einstein's magnificent rules, are subtly incomplete. On the scale of galaxies, where gravity is incredibly weak, the force might behave differently than it does here in our solar system. MN proposes a slight modification to the math, a tiny adjustment that would make stars on the outer edges of galaxies orbit just as fast as those near the center, matching what we observe without invoking any unseen dark matter. It is a bold claim that we have misread the universe's handwriting, mistaking a change in the rules for a missing ingredient. Deep space navigation in 2026 provides a critical test. The outer solar system is the frontier where the sun's grip begins to truly fade. It is the perfect environment to see if gravity, in its weakest regime, still obeys the old rules. By tracking our farthest flung spacecraft with relentless precision, we are conducting an experiment of cosmic scale. A confirmed anomaly in their flight would be like finding a single, mislaid puzzle piece that forces us to reconsider the entire picture on the box. It would suggest that the strange motions of galaxies are not due to some mysterious shadow substance, but are instead a reflection of a deeper, more nuanced law of gravity that applies everywhere. The implications would ripple through every mystery we have discussed, potentially rendering the search for dark matter particles unnecessary and forcing a complete rewrite of cosmic history. The quiet journey of a spacecraft into the black becomes a referendum on the nature of reality itself. This profound silence from the cosmos is perhaps the greatest mystery of all. We call it the Fermi paradox, named for the physicist Enrico Fermi, who, over lunch one day, posed a deceptively simple question. If the universe is unimaginably vast and ancient, with hundreds of billions of stars in our galaxy alone, and many of those stars are older than our sun, then where is everybody? The math seems to shout that we should not be alone. The Milky Way galaxy is over 13 billion years old, more than enough time for even a single, ambitious civilization to arise and spread across its entire breadth, colonizing star after star over millions of years. By that logic, their artifacts or signals should be everywhere, as obvious and unavoidable as ancient ruins on a well-traveled continent. Yet when we listen, we hear only a cosmic quiet. When we look, we see no obvious megastructures blotting out stars. This glaring contradiction between high probability and zero evidence is the heart of the paradox, a philosophical puzzle that haunts our search for meaning in the cosmos. The year 2026 brings fresh data to this ancient question, not from listening for signals, but from refining the very equation that frames our optimism. This is the Drake equation, an elegant formula that tries to estimate the number of communicative civilizations in our galaxy. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, and the probability that life emerges, becomes intelligent, and builds technology. For decades, most of these numbers were pure guesswork. Now, thanks to the exoplanet revolution, we are filling in the blanks with hard data. We now know planets are not rare, they are commonplace. We are beginning to understand how many of those worlds orbit in the temperate zones of their stars. Each new discovery from telescopes like James Webb and future missions like the Habitable Worlds Observatory will plug more precise numbers into the equation, tightening our estimate of how many potential cradles for life are actually out there. But this scientific progress leads us directly to the paradox's most unsettling implications. If the galaxy is truly filled with so many promising worlds, then something must be stopping life from reaching the stars. This idea is known as the Great Filter. It suggests there exists at least one catastrophic, nearly insurmountable step in the evolution from simple chemistry to a spacefaring civilization. The terrifying question is, where does this filter lie? Is it behind us, meaning the step from non-living matter to simple life is extraordinarily rare and we are a miraculous fluke? Or is it ahead of us, waiting in our future? This second possibility is deeply sobering. Perhaps the filter is the transition to technological maturity itself. Maybe every civilization, upon discovering the power to manipulate atoms and energy, inevitably turns that power upon itself through war, or creates technologies that spiral out of control, like artificial intelligence or engineered pathogens. The Great Silence, then, would be the echo of countless civilizations that flashed into existence and then vanished, leaving no trace but empty, habitable worlds. Yet there are other, less bleak solutions to the paradox. One is that we are simply too early. We live in a relatively young universe in terms of complex life. The most long-lived, stable stars for life are smaller, dimmer red dwarfs, which can shine for trillions of years. Civilizations arising around such stars in the far, far future would have an immense head start on cosmic timescales. We may be among the first primitive arrivals to the party, waiting for others to show up. Another idea is that we are looking for the wrong things, or that they are too different to recognize. An advanced intelligence might not use radio waves, considering them primitive noise. Their technology might be so seamlessly integrated with their biology and environment that it is indistinguishable from nature to our eyes. Or perhaps they are here, observing us with a patience and subtlety we cannot perceive, following a principle of non-interference with developing cultures. The data we gather in the coming years will not solve the Fermi paradox, but it will sharpen its edges. Every new exoplanet atmosphere analyzed, every failure to detect a technosignature after a more powerful search, and every deeper understanding of how life begins on a molecular level, each piece of evidence pushes the probable location of the Great Filter. Are we a cosmic miracle, a tragic precursor, or simply a child shouting into a galaxy that is not yet listening? The silence itself is the answer, and we are only now learning how to understand what it is trying to tell us. That profound silence makes one brief, 72-second burst of sound all the more tantalizing. In the archives of the search for extraterrestrial intelligence, one event stands alone, a single, perfect candidate that has never been matched or explained. It is known simply as the WOW signal. On the night of August 15, 1977, the Big Ear radio telescope at Ohio State University was silently scanning the sky. its data printing out line by line on continuous fanfold paper. An astronomer named Jerry Amon was reviewing the printout days later when his eyes locked onto a sequence of letters and numbers from a narrowband frequency. The signal was so powerful, so perfectly artificial in character, that he circled it in red pen and wrote a single, emphatic word in the margin: "Wow." The signal came from the direction of the constellation Sagittarius, near the star group Chi Sagittarii. It lasted for exactly 72 seconds, the precise duration the Big Ear telescope could hold a fixed point in the sky due to Earth rotation. It was a narrowband radio burst, meaning it was concentrated on one specific frequency, just like a tuned radio station, unlike the broad, noisy emissions of natural cosmic objects. Most critically, its intensity rose and fell in a perfect bell curve, exactly as you would expect for a distant, fixed source passing through the telescope's stationary beam. It matched the hypothetical profile of an interstellar beacon in every technical detail, and then it vanished, despite decades of follow-up observations by countless telescopes. Listening intently to that same patch of sky, the signal was never heard again. It was a cosmic one-night stand, a shout into the dark that received no reply. For years, the WOW signal has existed in a state of tantalizing limbo, the best evidence we have that is not evidence at all. It could not be verified, so it could not be claimed as a discovery, yet its perfect characteristics made it impossible to simply dismiss. The year 2026, however, brings new tools to this old mystery, not with new listening campaigns alone, but with a forensic re-examination of the past. Advanced data analysis techniques and artificial intelligence are now being applied to old radio telescope archives, sifting through terabytes of historical static with algorithms far more sensitive than the human eye. These AI systems are trained to recognize incredibly subtle patterns, to separate the needle of a potential signal from the haystack of terrestrial interference and natural cosmic noise with a precision that was science fiction in 1977. Researchers are methodically scanning the same region of Sagittarius, but with modern radio arrays that offer vastly greater sensitivity and the ability to monitor multiple frequencies simultaneously. The goal is twofold: to either catch a repeat of the signal, finally confirming its origin, or to definitively rule out every possible natural explanation. Could it have been a reflection of a human transmission, bounced off a piece of space debris? Could it have been an unknown, ultra-rare astrophysical event, a one-off radio burp from a star or a comet? Each hypothesis is being tested against the data with modern computational power. If a natural source is identified, it would finally close one of the most famous chapters in SETI history, a lesson in humility and the perils of cosmic coincidence. But if, after all this renewed scrutiny, the WOW signal remains stubbornly unexplained, its status will only grow more profound. In a universe filled with fast radio bursts and flaring magnetars, its unique, narrowband, clean signature would still stand apart. It would endure as the purest anomaly, the one signal that looked exactly as we predicted an intelligent message would look. Its enduring mystery serves as a quiet reminder that our search is not futile, that the cosmos might indeed speak, but perhaps only once, in a whisper we must be supremely lucky and prepared to hear. The universe's grandest mysteries may be written in its smallest script. While we search for dark matter and listen for alien signals, a quieter revolution is unfolding in the realm of the infinitesimal, where the bizarre rules of quantum mechanics reign. Here, particles can be in two places at once, influence each other instantaneously across space, and behave as both waves and particles. These are not just abstract curiosities, they are the fundamental code of reality, and we are on the verge of testing that code on the largest canvas imaginable, the cosmos itself. Space is becoming the ultimate quantum laboratory. The profound, quiet, and sustained freefall of orbit offer conditions impossible to achieve on Earth, allowing us to isolate and observe quantum phenomena with a purity that could finally bridge the chasm between the tiny quantum world and the vast force of gravity. In 2026, experiments aboard the International Space Station are pushing this frontier. At the heart of this effort is NASA's Cold Atom Lab, a facility no larger than a small refrigerator that is doing something extraordinary. It uses lasers and magnetic fields to chill clouds of atoms to a temperature just a whisper above absolute zero, colder than the void of deep space itself. At these temperatures, atoms slow to a crawl and merge into a unique state of matter called a Bose-Einstein condensate. In this state, millions of atoms lose their individual identities and behave as a single quantum wave, a superatom. On Earth, gravity pulls on this fragile quantum cloud, causing it to sag and distort, limiting how long scientists can study it before it dissipates. But in the microgravity of the space station, that pull is gone. The condensate can float undisturbed for much longer periods, allowing researchers to observe its delicate quantum properties with unprecedented precision. This is not just about setting records. By studying how these ultra-cold atoms behave in freefall, scientists can perform exquisitely sensitive measurements of fundamental forces, search for subtle deviations from the known laws of physics, and even simulate complex quantum systems that are impossible to model on supercomputers. Yet one quantum phenomenon stretches the imagination furthest: entanglement. This is the spooky connection, as Einstein called it, where two particles become linked so intimately that measuring a property of one instantly determines the property of the other, no matter how far apart they are. It defies our classical intuition about locality and information, suggesting a deeper, hidden layer of connectedness in the universe. Laboratories on Earth have entangled particles across distances of over 100 kilometers, but space offers the ultimate testbed. Imagine establishing an entangled link between a particle on Earth and one on a satellite, or between two satellites separated by thousands of miles. Such experiments would rigorously test the limits of quantum mechanics over truly astronomical scales, probing whether this ghostly connection holds firm across the gravitational curvature of spacetime itself. This brings us to the greatest puzzle of all, the missing link between quantum mechanics and gravity. Our two most successful theories of reality are fundamentally incompatible. Quantum mechanics describes the wild, probabilistic dance of particles and forces, while Einstein's general relativity paints a smooth, geometric picture of gravity as the curvature of spacetime. They work perfectly in their own domains, but they break down when forced together, such as at the singularity inside a black hole or at the moment of the Big Bang. To truly understand the universe, we need a theory of quantum gravity, a single rulebook that governs everything from the spin of an electron to the orbit of a galaxy. Experiments in space may provide the first clues. Some theories suggest that the fabric of spacetime itself might have a subtle quantum foaminess at the tiniest scales, a seething sea of virtual particles and wormholes. While we cannot peer directly at that scale, its effects might subtly influence quantum systems in predictable ways. By performing ultra-precise quantum measurements in the pristine environment of space, far from the seismic noise and magnetic interference of Earth, scientists hope to detect whispers of this underlying graininess. They are looking for tiny anomalies in how entangled particles behave or how matter waves interfere that could only be explained by gravity playing a quantum role. The data gathered from stations like the Cold Atom Lab in the coming year is a direct probe into this unknown. It moves us from philosophical speculation into the realm of hard evidence. Each successful experiment in orbit is a step toward answering the most profound question in physics. How does the universe truly stitch together the very small and the very large? The answer will not come from a telescope or a particle collider alone, but from the silent, delicate dance of atoms in the weightless dark, a dance that holds the secret to everything. Far beyond the last whispers of the sun's warmth lies a ghost. It is the Oort cloud, a vast and silent shell of frozen relics that marks the true boundary of our solar system's influence. This is not a place you can point a telescope at and see, not a bright band like the asteroid belt or a populated disk like the Kuiper belt. It is a theoretical realm, a sphere of icy planetesimals that begins roughly 2,000 times farther from the Sun than Earth and stretches perhaps halfway to the nearest star. We have never directly observed a single object within the Oort cloud, yet we are certain it is there. Its existence is written in the long, looping paths of comets. When a comet with an orbital period of thousands or even millions of years suddenly swings into the inner solar system from a random direction, it is a messenger from this distant, frozen vault. Something, a gentle nudge from the gravity of a passing star or the collective whisper of other icy bodies has dislodged it from its deep freeze, sending it on a million-year fall toward the Sun. The Oort cloud is the solar system's attic, storing the pristine leftover building blocks from our formation over 4.5 billion years ago. Each long-period comet is a piece of that original material, thawing for the first time as it approaches our star, offering us a taste of the ancient ingredients from which our planets were made. But the cloud itself remains a silhouette, inferred only from the trajectories of these rare, icy visitors. The year 2026 brings us closer than ever to glimpsing the shape of this ghost. While we still lack the technology to see the countless smaller icebergs in that distant sea, we are on the cusp of detecting its giants, the largest denizens of the Oort cloud, hypothetical worlds perhaps the size of Mars or even Earth, have been dubbed Oort cloud objects or OCO. These would not be traditional planets but dark, cold spheres of ice and rock, so far from the Sun that they reflect almost no light. Finding them is a monumental challenge, like spotting a lump of coal in the pitch black of a cavern a mile away using only a single candle. Yet our new eyes on the cosmos are becoming sensitive enough to attempt it. The Vera C. Rubin Observatory's all-sky survey is not just looking for Planet 9, it is scanning for any slow-moving, ultra-faint points of light in the extreme outer solar system. Its repeated, deep observations will create a map of motion, flagging anything that shifts position against the fixed background of stars over weeks and months. An Oort cloud object, if one exists within the survey's range, would move with an agonizing slowness, taking years to traverse even a tiny fraction of the sky. But the Rubin's decade-long mission is designed to catch that glacial drift. Simultaneously, improved astrophysical models are refining our search. Astronomers are running sophisticated simulations that trace the gravitational history of our solar system, modeling how the giant planets scattered debris outward in its violent youth, and how the gentle tug of the Milky Way galaxy and passing stars has sculpted the Oort cloud over eons. These models predict not just that the cloud exists, but suggest its density and how its objects might be distributed. They hint that the cloud is not a uniform shell, but may have lumps and streams within it, gravitational echoes of stars that brushed past our system millions of years ago. In 2026, the first indirect evidence for this structure may emerge. By analyzing the precise incoming paths of newly discovered long-period comets with unprecedented accuracy, scientists can run their orbits backward. Instead of just confirming they came from the general Oort cloud, they might be able to trace them to specific regions within it. If several comets arriving over a few years appear to originate from a similar distant point in space, it would be a smoking gun. It would suggest a gravitational disturbance in that specific part of the cloud, perhaps the wake of a recent stellar passage, stirring up material like a ship passing through calm water. This would be our first map of an invisible frontier charted by the paths of icy projectiles. Why does this matter so deeply? Because the Oort cloud is our solar system's birth certificate and its time capsule. The objects there have been in a deep freeze since the dawn of our planetary system, untouched by the heat of the sun or the geological churn that altered the inner planets. Their composition is a direct sample of the primordial nebula from which everything formed. Understanding the cloud's population and structure tells us about the conditions in our stellar nursery. Was it crowded, with many sibling stars forming close by whose gravity helped fling material outward to form the cloud? Or was it more isolated? Furthermore, the Oort cloud is a sensitive gauge of our galactic environment. By studying its shape and how it has been perturbed, we can reconstruct a history of which stars have drifted near us and when, reading a celestial guest book written in gravity. Finding even one large Oort cloud object or mapping a single stream of comets to a common origin would transform this ghostly concept into a tangible, dynamic structure. It would complete the map of our cosmic home, from the fiery heart of the sun to the frozen, silent frontier where our sovereignty ends and the true interstellar void begins. We are not just searching for icy rocks, we are searching for the outermost walls of our home and the ancient history locked in their frozen foundations. The final mystery is woven into the very fabric of everything we see and feel. It is the nature of time itself. We experience time as a relentless one-way flow, an arrow flying from the past through the present and into the future. But is that flow real, or is it an illusion of our consciousness? Physics presents a startlingly different picture. In the equations of Einstein's relativity, time is not a river. It is a dimension woven together with the three dimensions of space into a single, four-dimensional block called spacetime. In this block universe view, the past, present, and future all exist simultaneously, laid out like frames in a film. Our journey from birth to death is a path through this static landscape, and our feeling of a moving now is just a trick of perception. This idea challenges our deepest intuition about existence. If the future is already out there, what does that mean for free will, for cause and effect, for reality itself? Research in 2026 is pushing at the edges of this enigma from two opposite directions, the impossibly large and the vanishingly small. Cosmologists are investigating the ultimate arrow of time. Why does time seem to move forward? The most compelling clue is entropy, the measure of disorder in a system. The universe began in a state of incredibly low entropy, highly ordered and dense, and has been becoming more disordered and spread out ever since. Our perception of time's direction may simply be us riding this wave of increasing entropy from the Big Bang toward a future of maximum disorder. But why did the universe start in such an ordered state? Some theories suggest our Big Bang was not the absolute beginning, but one event in a much larger, cyclic cosmos. The search for gravitational waves from the earliest moments of inflation could provide clues, testing whether time had a true starting point or has always been. Meanwhile, in the realm of quantum gravity, physicists are wrestling with concepts that make time even stranger. To reconcile gravity with quantum mechanics, some theories suggest that spacetime is not fundamental. It might emerge from a deeper, more basic layer of reality, like the smooth surface of a lake emerging from the chaotic motion of countless water molecules. If true, then time itself may be an emergent property, not a primary ingredient of the cosmos. This research probes the most extreme environments where our concepts of time break down completely, inside black holes. At the heart of a black hole lies a singularity, a point where density becomes infinite and the laws of physics, including our understanding of time, cease to function. Understanding what truly happens there is the key to unlocking a theory of everything. Some speculative solutions to Einstein's equations even allow for closed time-like curves, theoretical pathways through warped spacetime that loop back on themselves. While these are likely mathematical curiosities rather than practical time machines, their very possibility forces us to question how rigid the arrow of time truly is. While we ponder these cosmic extremes, we are also testing the nature of time with astonishing precision right here in orbit. Networks of atomic clocks on satellites, like those in the GPS system and on the International Space Station, are not just for navigation. They are exquisite scientific instruments. These clocks are so precise that they can detect the subtle time dilation predicted by relativity. The fact that time ticks slower in a stronger gravitational field and for objects moving at high speed. By comparing the time kept by a clock on Earth with one in orbit, scientists verify Einstein's predictions to incredible accuracy. But they are also looking for something more profound, tiny deviations from the expected. Is the ticking of these clocks perfectly constant across all of space and time? Or are there minuscule variations that could hint at underlying changes in the fundamental constants of nature? If the strength of forces or the mass of particles were subtly different in the distant past or in another part of the cosmos, it would leave a fingerprint on the steady beat of atomic time. Finding such a variation would be a revolution. It would mean the laws of physics are not eternal and unchanging but could evolve with the cosmos. The fabric of reality itself would have a history. So, what is time? Is it a fundamental river, an emergent illusion, or a fixed dimension in a block universe? The investigations of 2026 will not give us a final answer, but they will tighten the constraints on our theories. With each precise tick of an atomic clock in space and each new insight into the primordial universe, we are not just measuring time. We are deciphering the substrate of existence, asking whether the stage upon which the cosmic drama plays out is static, dynamic, or something beyond our current imagination. The sheer scale of these questions is humbling, yet it reveals something extraordinary about our place in the cosmos. From the hidden oceans of distant moons to the phantom force of dark energy, from the quantum fabric of spacetime to the silent frontier of the Oort cloud, each mystery represents a frontier of human understanding. We are not passive observers in a finished universe. We are active participants in a grand, ongoing investigation, and the year 2026 is poised to be a landmark chapter. The tools for this exploration are now real. The immense mirrors of new telescopes, the delicate instruments of deep space probes, the silent arrays listening on the far side of the moon. These are not just machines, they are extensions of our curiosity, our desire to know what lies in the dark and how the story of everything truly unfolds. This era is unique. For the first time in history, we have the technology to move from speculation toward answers on so many profound fronts simultaneously. Whether it is a chemical whisper from an exoplanet's atmosphere, a precise map of dark matter's cosmic web, or a single, unexplained signal from the void, each piece of data is a step toward rewriting our cosmic address. So, stay curious, follow the news of these missions as their data streams back to Earth. Remember that you are living in a moment of unprecedented revelation, a time when the universe's deepest secrets are beginning to yield. Which of these mysteries captures your imagination the most? Is it the potential for life on Europa, the hunt for Planet 9, or the mind-bending nature of time itself? Let us know in the comments and subscribe to join us on the next journey into the unknown. The universe has been waiting to tell its story, and we are finally learning how to